Kia ora. In this video we're going to take a quick look at Simpson's rule. Simpson's rule is one of a number of numerical methods that you can use for doing definite integrals. Simpson's rule is suitable for cases where you have a function that you want to integrate, but you don't know how to, but you can't integrate it analytically. It's not so good for working with data. You're better off to use something like the trapezium rule or the midpoint rule for that. But if you've got a function like, I don't know, e to the negative x squared or something that you can't integrate analytically, Simpson's rule is going to give you a really good result. So we're going to do an example where we could actually do this analytically, so we can compare our result with the actual answer. So here's the problem we're going to do. Let's just quickly integrate this and find the analytical solution first, before we move on to doing it with Simpson's rule. So the analytical solution is basically integral, so that's just x to the negative a half, so integrate that, we're going to get 1/2 x to the half, so it's going to be 2 x 2 root x between 1 and 4, which is going to be 2 root 4 minus 2 root 1, which is just 4 minus 2, which is just 2. Okay, so whenever we do a numerical method on this problem, we are hoping to get an answer of 2 at the end. The other thing we can do is we can work out an error bound for how bad our error is going to be with Simpson's rule. But the slightly irritating thing about that is you need to know the fourth derivative of our function before we can actually find out what this bound is. So maybe we'll jump straight into doing the Simpson's rule on the computer first, and then we'll come back and see if the amount of error we get is consistent with this bound. So we'll do it for two different values. We'll do it for n equals 6, and we'll do it for n equals 12. Right, so I'm just going to hop out of this for a second, jump across to a computer. I'm going to use Octave, which is programming language a bit like MATLAB that you may have met if you did 160-102. Okay, so we're doing 1 over root x between 1 and 4. So let's just, and we're going to have n equals 6 to start with. So that means 6 intervals. You need to have an even number of intervals for Simpson's rule to work, because it basically creates a quadratic over each pair of intervals. Right, so we're going to start at, we'll say a equals 1 and b equals 4. Those are our endpoints. And we're going to need some x values, so we'll just use a command called linspace, which produces linear spaced elements, starts at A, ends at B, and we want 7 of them actually, because 6 intervals means there are actually 7 points. It's going to be n plus 1. There they go. And let's get our function values on those points. So that's just going to be 1. In Octave or MATLAB, you've got to use dot for dividing when you're dividing by a vector of things, and it's going to be the square root of x. Those are our function values. We also need to have our little delta x, which is 0.5, so we'll call it, you can also calculate that from b minus a over n, so that'll be 0.5 for us. So Simpson's rule is just a sum, and so if you're doing it on a computer, you can do it in one line really. Let's call it S6, because we're going to use 6 things there. It's going to be dx over 3, that's part of the Simpson's rule thing, times, now it is the first entry of x by itself, and then we're going to take the next, every second one from there onwards, and add those up and multiply by 4. So it's going to be 4 times the sum of f of 2, and we're going to go in steps of 2, and we're going to go to, let's see, 1, 2, the second to the end entry. And then for the other entries, the odd numbered ones, we're going to go 2 times the sum of those, so it's going to be f of 3, step 2, and that one's going to end at 2 from the end, again in steps of 2, and then we have to add on our final entry, and that should give us, just checking my brackets matching, hopefully an approximation of our integral, 2.005, and let's just change the format so we get some more decimal places. Do that calculation again, and we get 2.004. I'll just make a note of that on my notes. Equals 2.00047. let's go 469. Let's just have a few decimal places. Clearly, we can see the answer. The error is about 5 times 10 to the negative 4. While we're here, before we jump back to the iPad, let's also figure it out for n equals 12. So let's just go through the same calculation again. This time I'll go n equals 12. I'll need to recalculate my x's. I will need to recalculate my f's. Maybe I'll put a semicolon on so they don't all print out. I will need to recalculate my dx, which should now be 0.25. That's good. And then I'll just go and do my calculation again. There it is. So let's just call that S12. And you can see that because of the way I've written it, because I used end instead of 6 or 7, this calculation should just work just the same. We've updated our dx, that's good. So let's do that again, and you can see that my error now is a lot smaller, and so for 12, I get 2.40000036. Right, let's shift back to the iPad. Okay, so we did Simpson's rule. That was fun. We just added a whole bunch of values together, and we got some numbers that were close to 2. And these are what we got. So let's now work out what the error bound should have been, and let's see if the answers we got were actually within that. If they're not, then it shows that we've made a mistake somewhere along the line. Right, so we need to know the fourth derivative, so we're going to need to do a little bit of scratch working just to work out our derivative. So let's just make a little bit of space and change colour and do it in here. So we've got f of x is equal to root x to the negative half. We need the fourth derivative, so let's just chug through some derivatives. F prime of x is therefore equal to negative 1 half x to the negative 1.5, or negative 3 over 2. F double prime of x will be equal to, multiply that by 3 over 2 is going to give us 3/4 x to the negative 5 over 2, negative 2.5. F triple prime of x, just differentiate again, negative 15 over 8 x to the negative 3.5, or negative 7 over 2. And finally, the one we actually care about is the fourth derivative of x. 7 15s is 70 plus 35 is 105. It's going to be 105 over 16 x to the negative 9 over 2. Okay, now we are on the interval between 1 and 4, and we know that x to the negative 9 over 2, that's a negative power of x, and that thing is going to get smaller and smaller as x gets bigger and bigger. So this term here is going to be largest when x equals 1. This is when we're looking between 1 and 4. So what we can say is that on 1, 4, our fourth derivative is going to be less than or equal to, well, when x equals 1, then it'll just be 1 over 5 over 16. In fact, the absolute value of that. So that's going to be our k, which means that our Simpson's rule error should be smaller than k, which is going to be 105 over 16, times b minus a, so that's going to be 4 minus 1, which is 3, to the power of 5. Now this formula, by the way, we're just giving it to you, but it does come from doing a Taylor series analysis on the Simpson's rule approximation, but we're just not going to worry about exactly where that came from. We're just going to go for it. And then it's going to be divided by 180 n to the 4. All right, so let's figure out what those numbers are for n equals 6 and n equals 4. So n equals 6. Just going to type that in the computer, and I will get 1 over 5 over 16 times 3 to the 5 divided by 180 times 6 to the 4. So for n equals 6, this is telling me my error should be less than 6.8 times 10 to the negative 3, so 0.0068. I'll just truncate that. And when n equals 12, I'll just replace that with a 12, I will get 4.2 times 10 to the negative 4. So my Simpson's rule error should be less than 0.00043. So what you can see here is that our Simpson's rule error for n equals 6, it should have been less than 0.006. But what we actually got was a lot better than that. We got an error of only about 4 times 10 to the negative 4. And similarly, when n was 12, our worst case error, according to the bound, is 0.00043. But we actually did better than that. We did like almost a factor of 10 better, and we got our error being about 4 times 10 to the negative 5. So it just emphasizes that this thing here does not tell you how big your error is. It just tells you what the worst it can be. And quite often when you actually do the calculation, your result might be a lot more accurate than that. There's no guarantee that it will be as bad as this, but it's just telling you that it's not going to be any worse. By the way, I mentioned at the start of the video that Simpson's rule is not so good for like doing an integral of measured data. I'll just quickly sort of show you why. So let's just say you've got some data, and because we've measured it, it's going to be maybe a little bit noisy. We're trying to find the integral or the area underneath that graph. But when you do Simpson's rule, what's basically happening is it is splitting the data up into groups of 3, and it's fitting quadratics to them. So it's basically saying quadratic here. I'll just change colors to emphasize what's happening. Then there'll be a quadratic through these 3. There's only one quadratic that can go through 3 points, and then a quadratic through these ones. And so because with data you don't know what the bound on the derivatives is, you can't really work out an error estimate. And so you get you can get this situation where you actually get quite a jagged looking curve, and what you're estimating you might actually get something worse than if you just use a more simple rule than like the trapezium rule. So for example, the trapezium rule, instead of integrating this shape, would be integrating, let's just get one more color, let's go for red. If I did this using the trapezium rule, it will integrate just basically with straight lines instead of these quadratic pieces, and we quite possibly will do better than Simpson's rule. So just Simpson's rule is best used when you're working with a function that you know the functional form of, you know the formula for it, but you don't necessarily know how to integrate it. Whereas if you're trying to integrate some actual data, go for either the midpoint rule or the trapezium rule is probably the best choice. Okay, that's enough for now. We'll see you next time. See you later.